Welcome to this webinar. Before we begin the presentation, I want to provide you with a few housekeeping items. On your screen, you will see a taskbar with icons. Each icon is assigned to a particular element of today's webinar. After the webinar is over, please take our survey to tell us how we've done. Throughout the presentation, you can network with others or submit questions to the speakers in the box next to the slides. Download resources from the folder icon. Today's event is being recorded and archived and will be available within 24 hours. For on-demand questions or comments, send us an email by clicking Email Us. If you experience any technical issues today, please refresh your browser by hitting F5 for a PC or Command R for Macs, or email webinars@bmpmedia.com for one-on-one support. And now I'm excited to turn it over to today's moderator.
Good afternoon and welcome to this webinar, how to achieve clean, dry, compressed air for food processing applications without sacrificing energy efficiency. This event, brought to you by Food Engineering, is sponsored by Kaeser Compressors, and I'm your moderator, Deborah Shug, Editor-in-Chief of Food Engineering Magazine. Thanks for joining us. Today's presenters are Neil Mehltretter and Werner Rauer. Neil is a certified energy manager and is Kaeser's engineering manager. He has conducted and overseen thousands of industrial compressed air studies and helped users achieve significant energy savings and operational improvements. He has authored several nationally published articles on compressed air system optimization and is a frequent presenter on energy efficient system design. In addition to his bachelor's degree in chemical engineering from the University of Florida, Neil is Air Master Plus certified, has completed the Compressed Air Challenge curriculum, and is a Master Certified System Specialist through Kaeser's Factory Training Program. Werner Rauer is Kaeser's Product Manager for Rotary Screw Compressors. He has a degree in mechanical engineering and has been with Kaeser USA for more than 30 years. Werner is a frequent speaker and writer on compressed air system technology and system improvement. Werner currently chairs the Rotary Positive Engineering Committee for the Compressed Air and Gas Institute. Please don't forget to submit your questions, and later in the program, our presenters will address as many as possible. Also, today's event is being recorded and archived on Food Engineering Magazine, or foodengineeringmag.com. And now I'm excited to turn it over to today's presenters, Neil Mehltretter and Werner Rauer.
Thank you, Deborah, and good afternoon, everyone, and thanks for being out there. Today, we'll discuss compressed air quality and how it impacts operating costs and production. We'll also present information about designing the clean air treatment part of your compressed air system for maximizing effectiveness while minimizing costs. Here's one way to break out the types of wasted resources in industrial production. These are all areas that plants aim to minimize to some degree. We'll see in this presentation how compressed air quality and selection of air treatment equipment impact all these areas. Compressed air is only one facet of plant operations. In some plants, it might play only a minor role, but generally, compressed air is mission critical in nearly every plant. It powers more than 70% of all manufacturing activities. If compressed air is not delivered at the right air quality and quantity, production costs increase as both plant equipment function and product quality can be compromised. A quick sidebar about energy here. Compressed air has a high energy cost, and unfortunately about 50% of it is wasted. So think of it this way. The typical plant has a 50% yield on the compressed air it produces, and compressed air is often the biggest user of power in the facility. If you had that kind of scrap rate on any other input, you'd be all over that problem. Air treatment decisions have some impact on compressed air energy consumption, and we'll discuss this later on. The larger energy savings in compressed air are to be found in addressing other issues like leaks, controls, and eliminating inappropriate uses of air. These aren't topics for today, but I mention it to make the point that if you are not looking at energy costs of your air system, you probably should be. Today's webinar will discuss ways of ensuring that your compressed air treatment is effective and how it can help reduce scrap and downtime as well as power costs. I'll explain the types of contaminants and touch on air quality standards before we cover the consequences of design choices, a bit on piping, some tips, and best practices. Then we'll have time for some questions. When we talk about air quality, we're aiming to reduce 3 categories of contaminants down to tolerable levels: particulates, moisture, and oil. There's a 4th category, microorganisms, but this is really a special category that most compressed air vendors don't address in the plant air system. Typically, specialists tackle it with sterile point-of-use filtration products. Particles are solid, such as dirt and dust. They can be picked up from the ambient air and ingested into the compressor inlet. For example, baking can be heavy with flour dust, and the dust will find its way into the compressor inlet. Another source of particulate contamination is downstream of the compressor piping. Downstream of the compressor, which is the piping. Rust and scale in iron piping can build up over time and then flake off and head toward those points of use. Werner's going to discuss later in detail about piping and contamination effects. Moisture in both liquid and vapor forms is a major concern. When the compressed air is heated and then cooled, moisture forms in and after the compressor. Depending on ambient humidity and temperature, this can be many gallons an hour. And it also depends on the size of the compressor as to how much condensate you're going to get. So from a food safety perspective, moisture can be a problem since it supports growth of microorganisms. Oils and other hydrocarbon compounds can be in either liquid or vapor form. They can be present in piston or oil-injected rotary screw compressors. It is common for them to be ingested from the ambient environment if solids, spray lubricants, or other volatile compounds are present. This is true whether you're using oil-injected or oil-free compressors. Also, in rare cases, oil-free compressors can ingest its own gear oil if the sump vent is too close to the compressor inlet. Later, we'll address economical ways to remove those contaminants. When designing plant air systems, people have different expressions to indicate the overall level of air quality needed. Shop air, plant air, CDA, or clean dry air, instrument air, etc. They run the gambit. These are commonly understood, but rarely are they well defined. Instrument air is a classic example. Many think it requires desiccant dryers, but it's not necessarily true. It depends on the ambient conditions. ISA S7.3 describes instrument air in terms of system design and specifications, but it's still rather broad as it does not prescribe specific levels of air quality. Note that the air quality must be met, or the air quality must meet the requirements of the user. So the burden is on the user to understand and be aware of the requirements needed for their application. This is similar to what's happening in the food industry. So sorry about that slide there. It looks like the picture was truncated. All right, so here's a set of specifications for compressed air quality. ISO 8573-1. So this sets classes for specific levels of particulates, water, and oil. Specifying the ISO class level for each contaminant can provide usable guidelines for selecting compressed air dryers and filters. You take a specific level from each of the 3 categories to give the ISO class. So, for example, ISO class 2.4.1 would be class 2 for particulates, class 4 for water, and class 1 for oil. and then you select dryers and filters to meet those specs. Look for equipment specifications based on ISO standard 12,500 testing, so that's a different standard than we just talked about. But be aware that your plant conditions are not likely to match the testing conditions. So ISO standard 12,500 is a testing condition versus ISO 8573-1. So air quality testing you may do will differ from the stated specs of the filters and the dryer. So just be aware of that. Okay, we're going to go ahead and hit pause here for a polling question. Do you know what your ISO 8573-1 air quality requirements are? Okay, so we're going to go ahead and move on here, and once we get the results of the polling question, we'll move on. All right, well, that's excellent. So we got some responses here, and it looks like overwhelming folks are not aware of what their ISO 8573 requirements are. So interesting. So hopefully we can shed some light on that here today. Now we're going to talk a little bit more specifically about the food industry. So to put it plainly, currently there's no specification or regulation about air quality in the U.S. The Food Safety Modernization Act, which is FSMA, is overseen by the U.S. FDA, and it requires companies to employ risk management strategies regarding foodborne illnesses, but does not provide any guidelines related to compressed air. You may have also heard of the Safe Quality Food Institute. That's SQFI. It's a non-government organization that helps companies implement and document their food safety program. This is a lot like ISO certification, if you're familiar with that process. Each company, they set their own standard for safety, and based on acceptable risk levels, and documents what measures it plans to take. So SQF then audits to confirm compliance. They publish the SQF codebook that broadly covers many aspects of food safety. This is a copy of the SQF code, which cites the same two advisories about compressed air in several places in the document. So 11.5.71, compressed air that contains or that contacts food or food contact surfaces shall be clean and present no risk to food safety. And 11.5.7.2, compressed air systems used in the manufacturing process shall be maintained and regularly monitored for purity. In the absence of specific guidelines, some compressed air equipment vendors and consultants are turning to guidelines being used in the UK and the United Kingdom. As a general rule, ISO class 2.2.1, that makes sense for direct contact air and high-risk indirect contact. ISO 2.4.1 works for low-risk non-contact air. The basic difference is that 2.2.1 needs a desiccant dryer and may also need a sterile filter for direct contact applications. Though the constant here is that both need equal particulate and coalescing oil removal. Also note that if you want to remove trace odors or taste of compressor fluids or ambient hydrocarbons, you need to go below class 1 for oil and use a carbon vapor absorber in addition to the coalescing filters, then gets you to that class 1. To summarize the definitions used here, direct contact is airs used directly in processing or transporting food and or containers. Non-contact is compressed air is exhausted into the ambient air near food preparation, production, processing, packaging, or storage. So what's the solution? If you know that a certain combination of dryer and filter models work well for your application, you can approximate the ISO classes by looking at the specs of those particular products. Then you have a specification you can use when you expand, replace, or replicate your air system. If you don't have an existing system to work from, use your network. Find plants with similar processes. Often, your compressed air equipment vendor has the experience with other customers, to know what works. In short, there are common practices based on experience, but there are plenty of people buying desiccant dryers and extra filters just because they've been told they're needed, or just to be safe. A key point is that once you pick your specs, be sure to maintain the dryers and filters so they perform to that specification. Now, I'd like to go in more depth on some best practices. Here we're going to discuss some common misconceptions when it comes to talking about air quality. So best practices and misconceptions kind of hand in hand, one to avoid and what to do. So misconceptions, they may seem innocent enough, but in the spirit, in the spirit of erring on the side of caution, what are we going to do? In reality, these kind of knee-jerk reactions can increase your cost significantly and not provide any additional protection. So we know air quality is really important. The plant can't tolerate contamination or downtime. So that means we should install any and every dryer and filter just to be safe, right? Well, the U.S. Department of Energy estimates that for a typical industrial facility, 10% of the electricity consumed is for generating compressed air. For some, it's as high as 30%. So what does this mean in the context of air treatment? Over-designing or having more components in a compressed air system than are necessary can lead to unnecessarily high electrical costs. This is on top of the extra capital costs and then subsequent maintenance costs for these same items. Finally, pressure drop. Each component adds to the system pressure drop, which means you need to dial up the pressure at the compressors in order to have adequate pressure at the point of use. We often call this the scream point, the point at which somebody in the plant says, I can't make whatever it is I'm making because pressure is too low. Keep in mind that every 2 psi increase translates to approximately 1% increase in compressor energy consumed. In this way, you're essentially compounding wasted money on electricity. Our next misconception is bigger is better. In practical terms, though, why spend more money for something you don't need? I'm certain that those guys aren't going to be able to finish that pizza by themselves. All right, larger dryers and filters, they won't remove more contaminants and give you better, cleaner air quality. You'll end up spending more upfront capital on the equipment, spend more every day on electricity, and spend more throughout the life cycle on maintenance. Werner's going to talk later on about the use of energy management controls for dryers, which can mitigate the electricity consumption for components of these costs, including such options with new dryers. So if you're including an energy management controller with new dryers, that's a great practice. But if you do oversize, then you're also losing floor space, which could otherwise be used in more productive ways. The key is to right-size your dryers and filters. You can do this by using correction factors. Correction factors are supplied by each manufacturer, and there are factors for dryers as well as filters. For the sake of sizing, make sure you go with the worst-case scenario for your installation, which is probably going to be your summer months. Take the factors for the operating temperature, system pressure, and the ambient temperature around the dryer. We're going to spend a little bit of time with this slide in regarding using correction factors. In this particular example, we're discussing refrigerated dryers. However, the correction factors can be used for desiccant dryers as well as filters. There's specific correction factors for each and each manufacturer, but we're showing you this particular one. In this example, we have 120 psi inlet. We have 110 degree Fahrenheit for the inlet temperature, and 95 degrees for the ambient air temperature. And these result in correction factors of 0.83 and 1.05. Keep in mind, refrigerated dryers are generally rated at 100, 100, 100. What does that mean? It's 100 degrees inlet temperature, 100 degrees ambient temperature, and 100 psi. So by using the top table, we go over to the 110 degree Fahrenheit column and then search the 120 psi row. And that's how we arrive at 0.83. The same principle follows for the ambient temperature. In this case, we're multiplying these factors by one another, and you get 0.8715. You can tell an engineer wrote this PowerPoint here. This means that at these conditions, the dryer is only going to have 87% of its nominal capacity to dry the air to a specific dew point. So next, you take the dryer's rated capacity, which in this case we're assuming is also 200 CFM that needs to be dried, and then you multiply it by the correction factor. So you compare this number, which now becomes 171, so we call it D rate, with your compressor's rating capacity. And you want to make sure that those numbers are either the same or that the dryer is rated for more than the compressor. But in this case, it's not. So what do we need to do? Well, we need to select the next size compressor. I'm sorry, not the next size compressor, the next size dryer, to ensure that it has enough to dry the 200 CFM to the required dew point. Be careful, because correction factors could be used to multiply against the compressor flow or divide by the compressor flow to determine its rating, and that can be tricky. For both refrigerated dryers and desiccant dryers, the ambient temperature and inlet temperature to the dryer have a very significant effect on the amount of compressed air the dryer can accommodate. 20 degree Fahrenheit increase in temperature as an approach temperature and inlet temperature to the dryer roughly results in the air holding 50% more moisture, which means the dryer will have to work harder to condition that air at higher temperatures. Hence, the need to oversize the dryer for such warm conditions. At this point in the webinar, I'd like to hand over the phone to Werner Rauer to take us through to the end.
Thank you, Neil. My name is Werner Rauer, and I'm Kaeser's product manager for Rotary screw compressors. I'd like to focus on the individual air treatment components and how they work together in a system. I'll also end with some tips for system design best practices. Our next misconception is more is better, meaning more or a higher level of protection. Think of it this way. If your garden has a rabbit problem, you'll build a fence. Will you spend the extra in time, material, and labor to build a 6-foot fence, or will you go with a 3-foot fence, which is appropriate for the job at hand? It's pretty much the same with your system. Choose the right components for your process. Much like the consequences of our other misconceptions, by over-treating your air, you will have higher capital cost and spend more on energy and maintenance. Just one example. 4 of the same kind of particulate filter in series are not doing a better job than one that is properly selected and maintained. And this also won't do anything to improve your product quality or reduce your scrap rate when compared to using the right selection of equipment for your application and monitoring key factors of air quality. Here's a common example of overtreating. Going with a desiccant dryer, or as Neil pointed out, a 2-to-1 air quality for the entire system when only a refrigerated dryer is needed, and there may only be a few minor applications that would require a desiccant dryer. That decision on when and where to use a desiccant dryer over the refrigerated dryer has to be the result of your analysis of every point of use application for compressed air in the food processing of your plant. Refrigerated dryers are capable of handling the vast majority of applications. They cost less to buy and to operate compared to a desiccant dryer. Desiccant dryers use purge air to recharge the desiccant bed, so you're losing compressed air for this operation. Plus, the desiccant will need to be replaced as a normal maintenance item, which can be expensive. They're really only necessary for moisture-sensitive processes like some food processing where bacteria plays a role, or when any part of the compressed air distribution is exposed to sub-freezing temperatures. Please be aware of the piping that's going inside your building through a freezer area, which will also be exposed to sub-freezing temperatures. One more item. Be very careful before you accept a minus 100 degree Fahrenheit pressure dew point specification and find out why a minus 40 pressure dew point just won't do. Our last misconception has to do with the type of compressor selected. Oil is bad. Do I need an oil-free compressor? But just because you have an oil-free compressor, that does not automatically guarantee that you will have oil-free air. You still need to have adequate compressed air treatment to control particles, moisture, and hydrocarbons that may be ingested outside the control of the end user or the compressor manufacturer. So what does it mean to have an oil-free compressor? It doesn't mean that there is no oil in the compressor. It means the oil doesn't come in contact with the airstream in normal operation of the compressor. Keep in mind, whatever is in the ambient air will still be ingested into the compressor inlet and flow through the compressor into your piping system. Filtration and drying are still necessary for clean, dry air and an oil-free system. Also consider that oil-free compressors are usually less efficient than oil-injected units. They also cost more upfront and they may have higher maintenance cost. But they could also be a wash or less cost based on the different designs, and also depends on the size of the units. That's not to say that they're a bad choice. They should just be properly applied. Examples of some possible appropriate applications would be direct food contact and in many pharmaceutical, electronics, and chemical processes. Now I think we have another cue here. What type of air compressor do you have in your system? Okay, I think the choices are there clear, and we will move on. I guess we may have not given it enough time, but I'll still want to see that let's keep on going, and then maybe there will be some more towards the end. Okay, so let's come to our final point, and this is true for systems with oil-free or oil-injecting compressors. Don't forget the piping. I have seen this too many times. The plants spend time and energy selecting, purchasing, and installing a bevy of compressed air treatment only to have the clean, dry air pass into an old, dirty piping system. Some piping materials are a source of contaminants that can flake off and migrate to the production equipment. If you need clean, dry air, I can suggest copper or aluminum. Stainless steel is also an excellent choice, but it's more expensive. It's typically only required for special applications. Whenever possible, piping should be sized and looped to reduce the overall air velocity and pressure drop. Size the piping with the future in mind. Otherwise, when you expand and add more compressed air to the system, the increased pressure drop can significantly affect your scrap rates. One more comment there. If you're planning on upgrading from a current lubricating system to an oil-free system, highly suggested to upgrade the piping, as most of the piping is as old as the building, some of them 30 plus years old. So it would be about time to upgrade that piping system. Now we will go into some specific steps of the compressed air treatment. This graphic shows the air treatment included in a typical compressed air system. We will go through each part in more detail, but there's one thing I want to point out before we go. There are no bypasses on any critical air quality systems. For 24/7 operations and for backup systems, we highly recommend parallel clean air treatment paths. So the first air treatment element in our system here is an aftercooler and a moisture separator. As you can see, I have the compressor highlighted here. For these components, this is because many compressors come with the aftercooler and moisture separator directly integrated into the package. If you have a compressor without these, like for example on a reciprocating compressor, also called piston compressors, then you will want to install one near the compressor discharge. One meaning the aftercooler with the built-in moisture separator. Next, we have an air receiver tank. I'm often asked where to install a receiver tank, and it honestly depends on what your goals are. In the setup here, we have a wet tank. This is installed after the compressor and before the air treatment. It functions to knock out additional condensed water due to the cool down of the compressed air. To help the air treatment after the tank function more effectively, you will want to make sure you have a functioning drain on the tank and to regularly check it's operating correctly. This type of tank should be sized as 1 to 3 gallons per CFM of storage in your system. It also acts as a buffer volume to allow for smoother compressor capacity control, sometimes also called a control receiver. The other option is to use the air receiver as a dry tank. This is installed after the cleaner treatment, and it creates storage to handle intermittent high demand events or surges. In order for there to be storage, though, the pressure must be higher than the operating pressure requirement at the point of use. Those tanks are typically sized at 3 to 5 or more gallons per CFM. In a perfect world, systems would have both a wet and a dry tank. However, this is not typically possible due to floor space restrictions. If that is the case for you, decide which is more of a priority, control or storage. With a master system controller for the compressors that sends the line pressure after the cleaner treatment, the dry tank is typically the preferred way to go. Next, we have the drains. These should be installed on receiver tanks, filters, and dryers. There are 3 basic types of drains: the manual, timed electric, and a demand type drain. The manual drains are exactly what they sound like. They're simply hand-operated valves and are only as reliable as the person who is responsible for checking them. They are inexpensive, but really not the choice for consistent and reliable moisture protection. The timed electric drains are set on a fixed timer to discharge and the break in between. This makes them a bit more reliable. However, they will always open when the timer goes off, even when there is no moisture present, therefore wasting compressed air. It's also important to adjust the timers for the season. They would need to open more often during the summer than in the wintertime. The time adjustment must be done manual, so it is easy to miss. So, bottom line, the best option would be a demand-operated drain. That type of drain is a bit more expensive. However, it only discharges when moisture is present, so the compressed air is not wasted. Also, some drains have additional contacts that can be connected to a system master control or to plant controls that would signal when there is an alarm. This is especially helpful for applications that cannot tolerate any moisture. The same signal can be used to close off the compressed air to protect the process from contamination. Remember, your clean air treatment is only as reliable as the weakest link, and that is typically the drains. Without reliable drains and moisture separators, tanks, dryers, filters, you run a high risk of contamination that you spend money to remove, building up in these components and getting downstream into production equipment. And with tanks, there are other negative impacts. Moisture can build up quickly in the tank, particularly in the summer months. The more water, the less room for storage. The less storage, the more your compressor will cycle on and off. This increases the wear and stress on valves, motor starters, air vents, and coolers. And the results? More frequent maintenance, repair and downtime, shorter machine life, and higher energy cost. So let's move on to the dryers, where we are showing here a refrigerated dryer. Another common option would be a desiccant dryer. There are other dryers available, let's say like an integrated option in a rotary screw compressor. Those are typically refrigerated dryers and are installed inside the cabinet that's attached to the compressor package. The oil-free compressors may also have the option of heat-off compression desiccant dryers, either built-in or external, using the heat of compression to regenerate the desiccant beds. Standalone dryers, regardless of what type they are, would be placed in the same spot in the system. From a system design point of view, the difference is in which filters are necessary to include with the dryer type and where those filters need to be installed. That means before or after the dryer or both. In this example, with refrigerated dryer, the oil removal filter would be either inside, called cold coalescing, or after the dryer. Different types of filters remove different kinds of contaminants. As Neil mentioned earlier, those contaminants include oil, moisture, and particulates. If you have a desiccant dryer, it will need to have additional filtration before and after the dryer. Install a particulate and an oil coalescing filter before the dryer. This is because the desiccant beds are highly sensitive to oil, and the desiccant will not be able to absorb moisture if even a trace amount of oil is present. After the dryer, be sure to include a particulate filter. This will catch any of the dust or desiccant fines. And now here is the big topic to consider for the food industry. If you are concerned about odor and taste, you have to include an oil vapor filter. To meet ISO 8573 Class 1 for oil, always include a vapor absorber. At the very end, there's also point of use filtration, which Neil mentioned earlier, typically consisting of particulate, liquid coalescing filters, and sometimes also sterile filters. We're not going into those, as those are part of your hazard or risk analysis, which you have to do for each point of use of compressed air. All of the moisture or condensate from the system needs to be disposed of. It cannot simply be drained into a sewer system. Having a condensate collection system like the one shown here will help you make sure you are following environmental regulations. The type of container shown here is connected to all of the drains, tanks, compressors, filters, dryers, and everything in the system that has some kind of a drain. It has a filter which then removes the contaminants to a safe level for the disposal. Make sure you consult your local code for guidance on the disposal regulations. One typical one would be less than 20 parts per million for hydrocarbons. The final component in our air treatment lineup is an air demand charging system. This valve essentially provides a controlled pressurization during startup to prevent high velocity air from overrunning all of your air treatment components. It is useful for systems that are shut down and restarted regularly. For example, the system that ran single or double shift or every startup at Monday morning. It is also useful for systems that have a high air quality standard but run 24/7. That will prevent the system to overrun the cleaner treatment. If the demand of the system exceeds the capacity of the compressors, the pressure would drop, and then you're overrunning your cleaner treatment. Finally, that same valve can also be used to close off the compressed air supply in case there are any alarms of the cleaner components like the drains, the dryers, or any additional alarms. A good choice would also be to add a pressure dew point alarm for your most critical applications. So now that we have discussed the individual components, I'd like to close with a few best practices tips. Tip number one is to think of your compressed air system in terms of zones. Break down the points of use and determine each of them need what they need in terms of pressure and air treatment. of course also flow. If you have a specific section that needs higher quality air, consider adding additional filtration near the application rather than treating the entire system as such. The same is true for pressure. It is much cheaper to treat an application instead of the entire system. Our second tip is to think about controls when selecting a specific dryer model. Two common modes of control are energy management and non-energy management. The energy management dryers match the energy consumption of the dryer to the demand of the system that is going through the dryer and are best applied when the system runs continuously and has varying demand loads. These are available in both refrigerated dryers and desiccant dryers, sometimes called cycling dryers on the refrige side, or dew point control on the desiccant dryers. A non-energy management type of dryer could be programmed for on-off times to meet specific shift requirements that would give you some energy savings during operation for the system that have a consistent demand that is close to the dryer capacity and run effectively. However, if the demand does vary, an energy management dryer would be recommended. Please don't forget that cycling refrigerated dryers will have a varying pressure dew point. Our last best practices tip is to think about communications capabilities. With the industry moving more and more towards the IoT or Internet of Things solutions, start planning now to be ready to integrate components or the complete system. Look for capabilities on dryers, filters, drains that enable communicating with air master controls or SCADA systems. Having this connection to a centralizing control system can enable alarm notification when there is a dryer or drain alarm, for example. If necessary, it can be programmed to shut the entire system down to prevent contamination due to an air treatment malfunction. This can help protect your products and reduce your scrap rate. In closing, there is a lot to keep in mind when determining the right air treatment components for your compressor system. Careful planning, though, can significantly reduce the life cycle costs, improve uptime, and reduce product scrap. Don't hesitate to engage a compressor expert to properly select the right air treatment solutions for your applications. So thank you for your attention, and now I believe we still have time for questions, and we're going back to Deborah.
Yes, thank you so much, both Neil and Werner, for your presentation today. Really appreciate it. And so, yes, as Werner said, we do have some time for questions, so I'd like to open the floor for that. Please make sure that if you have a question, to submit it for our presenters to address. And so we do have some questions that already came in during the presentation, so I'm going to go ahead and ask some of those. Our first question is, would it ever make sense to have two systems in a plant, one for where air specifically comes in contact with food and one where it doesn't come in contact with food? What do you guys think about that?
Yeah, I mean, we certainly spend quite a bit of time to talk about not to overdo it. And one of the solutions certainly is to have two different systems. We have plenty of customers and applications where we have both a lubricated system for a specific part of the plant. There's also some statistics out there that say that about 50% as an average on the food industry, there is definitely a non-food application for air. So it all depends on where the bulk is of the air usage. You should do your cleaner treatment on that. And then if you have individual lines where you need a better filtration, you may either add your cleaner treatment there, or you may even have to, for whatever reasons. Sometimes there are custom requirements from your the end users or the customers of these food plants. They require, for whatever reason, that you run this process with an oil-free compressor. So there are systems out there that are having oil-free compressors on top of their normal lubricated systems, just in order to meet that demand and that requirement.
I see. Okay, thank you for that. This next one is more sort of a statement, but just curious to get you guys' opinion of what you think about this comment. So it's regarding, so you did talk about over-design of the compressed air system. So this viewer says it's quite challenging to know what is a worst-case scenario for loads and over-design related to air treatment. Because most food processing or pharma facilities can't afford a shutdown or recall versus having cleaner air. So what do you guys think about that, the balance between, you know, having enough and over-design? Just putting it out there for you guys.
Yeah, thanks, Deborah. It's a great question. This is Neil. I'll start it, and I'll ask Werner if he has anything to add. But, you know, from an over-design standpoint, there's a couple things to consider. You know, Werner said this already about no bypasses, and that kind of, he also mentioned about backups. So from a certain standpoint, dryers and filters, you know, when we talk about downtime, we usually talk about 100% redundancy. So if you have, let's say, one dryer, whether it be desiccant or refrige dryer, you have one that's sized for the entire demand. The recommendation, you know, for us is always, you know, and the user here, the question person who submitted the question is absolutely right. You know, a recall or you know, downtime is going to cost a numerous more than adding a backup dryer and or filter. So from my perspective, you know, if you are looking at, say, 100% redundancy, then yes, I would definitely, I would suggest that for sure.
Okay, I'm going to add a few more things there. Number one, as we mentioned earlier, it is the food manufacturer's responsibility to make a hazard and risk analysis. So this is where you come up with like which part and which process needs what kind of quality of air. Once you have established that and you have a beautiful design where there's a lot of people who can help you with that, who have this experience about that type of application, that kind of quality, but then I think at the end of the question you say, well, how can I sleep at night to be sure that I do get this quality? And there are numerous ways to kind of get that feeling about sleeping well. At least one of them we mentioned about the alarms and then closing of a valve. If you really have a super interest in the air quality there are sensors out there, online sensors that are continuously monitoring, and depending on your degree of sleep or not sleep, you have to spend quite a bit of money for any leftover hydrocarbons or oil in the compressed air. It is very easy to do a pressure dew point nowadays. There are sensors out there that are very inexpensive, and you can put them actually in multiple areas. The particle count, that's a little bit of a two-sided sword. Typically, most of the applications is not that critical, but for those that are, there are some, let me just say, $40,000, $50,000 sensors that can actually do this as an online one. There's also a requirement or recommendation that the food processing plants that they have to have at least a yearly or sometimes biannual inspection of the air quality. It all depends on how critical and what the damage is in terms of monetary and to your customers. That's what determines on what compressor type, what cleaner treatment, and what kind of monitoring do I have to employ to be able to sleep at night.
Okay. Thank you for that. So this viewer is curious, have you seen anyone get cited for contact air not being clean enough? I'm
not aware. I have seen annual audits at some food processing, like bottling beverage companies. I'm not so sure why somebody's asking that, so I cannot really comment on that other than that at the end, it's your responsibility as the operator, and if it would be me and these are my customers, I would do whatever I can to make sure that whatever they expect from my products, that's what they're getting, and that for me would include a monitoring in order to prevent this kind of situation.
Great. This viewer has a question. What system is more costly to maintain, an oil-free compressor or a lubricated machine with food-grade oil?
I mean, I think we touched a little bit on it. Okay, so the oil-free compressor, we said, costs more, and when I say costs more, it's quite a bit more. It could be more than 50%. The compressor itself is less efficient to operate. It means your energy cost to get the same amount of air at pressure will be 7 to 20% higher. Some people might say that the cleaner treatment that's required for the lubricated one would be offsetting that. That's not quite true because, as we stated, any compressor type would require a certain type of cleaner treatment. So for me, this is almost a wash. So at the very end, in terms of operating costs, I think we addressed this there, that an oil-free system with an oil-free compressor is a higher cost to operate than a lubricated one.
But to Werner's point, which he already mentioned, it's what allows you to sleep at night the best, and then what's the specification from an end user, or if you're a major manufacturer, what's the overarching goal or stipulation from your company? Does your company say it has to be oil-free, in which case then you really have no choice in that matter? It's a good question.
So kind of related to that, if you could go over the acceptable compressor oils for food-grade applications, which ones are the acceptable compressor oils?
So, okay, let's go back to the myth about oil-free compressors. Let's talk about oil-free rotary screw compressors. There's as much oil in those compressors as it is in a lubricated machine. It's just used for different purpose. Instead of mixing it with the compressed air, it's just simply used for lubricating of bearing and the seals, and to also do the jacket cooling on air-cooled machines. However, bottom line about the type of oil. First of all, they're typically all synthetics. There's a H1, H2. H1 would be for food grade. There are plants where you're not allowed to use anything but food grade lubricants. So that would be eliminating any other lubricants, and it would be an H1. But there are still plenty applications out there, I would say the vast majority, where this is not a requirement. But if you go into anything that is direct contact, food grade oil, if anything, is there. And for low risk, certainly you can use an H2 lubricant for that. But in most cases, these people are working with a food grade lubricant for the high risk applications, despite the cleaner treatment.
Okay, great. Thank you very much. So this here has a specific question related to something you said. He's asking why don't use a particulate filter prior to refrigerated dryer?
Yeah, this is Neil. I'll answer that because it came up when Werner was presenting, and I saw the question pop up. So what's interesting is some of the things that we use are from our parent company, and in this case the tank that's in this picture is a galvanized tank. In this country, we're just using standard tanks, which maybe there's an epoxy coating internal to the dryer, maybe there's an internal paint. The dryer to the tank, and maybe there's an epoxy coating, maybe there's an internal paint to the tank. In most cases, that's not the case. So it's a great observation, let's say, and in which case, in regard to piping as well as tanks, from a certain standpoint, if you're inducing any other potential, such as black iron over time, you're going to rust and scale, or the tank, if it's not a galvanized receiver, or if it's not internally powder coated or epoxy coated, then you can have issues over time. So it's a great question. In general, I would say if you have a wet tank and it's not coated, definitely have to have some kind of filtration to protect that dryer. And then also the type of pipe that's used. We showed blue pipe in there, which is aluminum piping. So you're not susceptible to corrosion with that. But if you do have some other type of piping, then I'd say yes, definitely something to consider.
Great, perfect. This viewer wants to know kind of a specific question as well. How do you size the flow rate for desiccant dual tower regeneration? Is it usually 30% of normal flow rate?
Okay, I'm not 100% sure whether I understand the question. A cold regenerated desiccant type dryer is typically in the 15 to 17% need of purge airflow. Neil went to some sizing on dryers. There's of course also sizing for desiccant dryers, and of course since you have more air going in than air coming out, you have to size the dryer for what you require downstream, and you have to add the purge requirement on top of it in order to A, size the dryer properly, and B, size the compressors properly.
I see. Okay. And so is there a way to test for contaminants in plant air?
What did you say? Is there a way to
Test.
Is there, yeah, do you want me to,
yes, okay. I think
we
we mentioned this earlier, but I know these questions come in as we said. Yes, the easiest one is pressure dew point, no problem. The requirement was annual or biannually that they do make a full test, which is also oil and particulates. The oil, depending on what your level is, it is easy all the way down to about 1 ppm. Anything below 1 ppm is not going to be that easy. Then you're talking about $10,000, $12,000 for an online sensor. They are certainly out there and they are available. I'm not saying any names, but they are certainly available. And there's also scattered laser light particle counters that are available. And I did mention something in they used to be 40 to 50,000, depending on how low you go. But there are also some available that are in the $20,000 range. So yes, certainly out there, but quite expensive if you really go into the very, very high quality of compressed air monitoring.
Aha, okay. Now here's another question that just came in. What is the life expectancy of food-grade oil versus normal synthetic oil?
That pretty much depends on which compressor we're talking about. On an oil-flooded rotary screw compressor, the oil and the air that's coming from the ambient is heavily intermixed. That means you have quite a bit of introduction or ingestion of contamination, which you have no control over, pretty much. So there, the lifetime depends on those type of ingestions, if it is oxidizers or any other like ammonia, that kind of things, which is unfortunately available at some of these food processing plants. Typically, they are ranging from anywhere from 3,000 to 8,000 hours. I say typically. I would say the average is between 4 and 6. We still recommend, of course, oil analysis. On the oil-free compressors, which we now learned that they have as much oil in there as the other ones, there it's a different story because you're using the oil pretty much for lubricating and sealing, meaning bearings and seals, and a little bit of the jacket cooling. So there, the challenges are a little bit different. Those compressors are running at much higher temperatures, so the stress on the oil is more or less the temperature and not so much the contaminants. So you still do your oil analysis, and those can reach anywhere from 6,000, maybe even past the 8,000 mark. It depends, of course, which type of lubricant. Everybody out there is saying they have the latest and greatest. Some say even 12,000 and more. I would just say buyer beware, and that's the end for me here on this comment.
Understood, understood. So we have a couple of minutes left. So in that time, just wondering if you could go over the importance of room temperature to air quality. What effects does that have on air quality?
Well, it's actually kind of huge.
Oh.
I mean, yes, temperature affects several things. Neil went over the sizing. The sizing of the dryer is critical with the ambient temperature for most of them, in particular refrigerated dryers. Another factor that sometimes gets forgotten, I mentioned that in food-grade applications on our 3 groups, you should always have an oil vapor absorber. The higher the temperature, the more oil can be in the air. If it's available, it will be there, and that would then reduce the lifetime of your oil vapor absorber. So those are the most important effects. Another effect, we just talked about the oil. The hotter the temperature, the lower the lifetime of the lubricant, if that has an impact on the operating temperature of the compressor. So ambient temperature is definitely a factor, and for refrigerated dryers and aftercoolers, that will also produce higher compressed air temperatures, which then stress a little bit more or increases stress on the cleaner treatments. This needs to be dealt with in the design phase, as Neil pointed out, and that's where compressed air experts can help you to make the right choice.
Great. Perfect. Well, it looks like that's about all the time we have today. So thank you everyone very much for your questions. And also please join me in thanking Neil and Werner for their presentation, as well as our sponsor, Kaeser Compressors. If you have any additional questions or comments, please don't hesitate to click the Email Us button on the console. As you exit today's webinar, please take a couple of minutes to complete our survey. We strongly welcome your detailed comments. Please visit foodengineeringmag.com/webinars for the archive of this presentation, as well as information about our upcoming events. We appreciate your time and hope you have found this webinar to be a valuable experience. Thank you, everyone.